Welcome back to Know How Right Now. Today I'm going to go over Newton's second law. So let's look at a problem. Suppose you have a worker, who knows, maybe somebody that moves boxes. In this case, somebody at FedEx or I don't know, USPS or something. Hang on. This guy decides to move this box here with the mass, and there's this velocity that goes over here to the right, and we know that in this particular case that the initial velocity is equal to 0. So let's write that down. Initial velocity is equal to 0. And we know that he moves this box from here to here in 6 seconds. And from here to here is 12 meters. So he moves it all the way over here. So let's list what we know. We know that the position that he moves it to is 12 meters and that the time is equal to 6 seconds. Now, with this information, can we find out? We also know that he pushes this box with a constant force of 90 newtons to the right. So, with this information, can we find the mass of the box? We can, right? So, let's get started. Let's use Newton's second law, which says the net force of the system is equal to mass times acceleration. And what are the forces on this? Well, let's draw a free body diagram. Okay, if we look at this box here, we know that there's mass times gravity, or just the weight going downwards. And then we also know that there's a normal force pushing upwards, or the earth or this dock here, whatever it is pushing upwards with the same force as the gravity. So these are equal and opposite forces. These are equal and opposite. So we can pretty much forget about those. Now, what other force do we have? We also have the force of this guy's push, right? So if this is the box right here, the push goes in this direction. He's pushing this direction, so let's say this is the force of the push. So, if we look at Newton's second law, it says that there's only one other force. Oh, and by the way, that's assuming that we can ignore the force of friction. If we can't ignore the force of friction, then that's a little bit of a different story. I mean, we can still use Newton's second law, but it's just a little bit of a different story. So now, Newton's law says that there's a foil. And by the way, I'm going to define the positive direction as this way. So the force of the push is going this way, so it's positive. So really this is a positive. If I said that it was positive going this way, then this would actually be negative, right? But it's positive. Force of push is equal to mass times acceleration. So now what? Well, we need to solve for m, right? So let's solve for m. And divide m on both sides. I'm sorry. We need to solve for m, so let's divide a from both sides. So now we have mass is equal to the force of the push divided by the acceleration. So we have the force of the push, but unfortunately we don't have the acceleration. So let's get to that. In order to find the acceleration, we have to go back a couple of chapters and we have to review kinematics. Now remember, there's an equation that says that the final position is equal to the initial position plus the initial velocity times the time plus 1/2 acceleration times time squared. Now, our system right here, this is x naught and this is x final, and we start at our we started at x naught is equal to 0. So if that's the case, then we can say x naught is equal to 0. So here's the origin. And we also say that where x naught is equal to 0, v naught is equal to 0. So we started at 0, the velocity is equal to 0. So this is 0. So all we're left with is x final is equal to 1/2 acceleration times time squared. So in order to find the acceleration, now all we have to do is solve for a. So let's go ahead and divide 1/2 on both sides, and we get 2x final is equal to acceleration times time squared. And we divide t squared on both sides, and we get that acceleration is equal to 2x final divided by t squared. And now we actually have all the values, don't we? Because we have our final x, which is this one right here. Started at x naught and it traveled 12 meters. So we have 2 times 12 meters divided by t squared, 6 seconds. And as far as the units go, this actually makes sense. Because this is going to be the units of acceleration is meters per second squared. And that's exactly what it's going to come out to right here. So let's use my little calculator right here. This isn't actually too hard here. 24 divided by 36, which is 0.67 meters per second squared. Okay, good. So now that we have our acceleration here, now all we have to do is plug it in right here. So in other words, our mass is equal to the force of the push, which is 90 newtons, divided by 0.67 meters per second squared. And that will come out to our final answer, which will be in kilograms. So 90 divided by 0.67. So the mass of the box is 134 kilograms. And this is an important thing here you want to know is that is the units here. So let's look at our unit work. Newton is equal to, here's our Newton. Newton is equal to kilograms times meters per second squared. And then here we just have meters. So if we divide if we divide our newtons divided by acceleration, then we take the units here, we divide those by meters per second squared, and what do you know? It comes out to kilograms. So it's a pretty interesting problem. I'm going to do a lot more of these Newton's second law problems because sometimes it's kind of hard for some people. But if you have any questions in particular, please let me know. But thank you for joining. Catch you later.